plus, so you got 3 chloride counteranions that are outer sphere, non-interacting with the cobalt center. But when L is a chloride, right, obviously this overall complex right here is 2 plus. The cobalt itself is still 3 plus, but this whole thing is 2 plus. So you have 2 chloride counteranions, right? Pretty straightforward, okay? You'll notice, and without showing you actual spectral data, you'll understand as you start to collect it. But you're basically going to have 2 major absorption maxima that you're going to see, and so you're going to record the wavelength of those 2 different absorption maxima. Okay, so the lower wavelength and the higher wavelength, and then so you'll have that in nanometers. You'll take that nanometers, turn it into a frequency in terms of inverse centimeters. And what you're going to look at here is you're going to actually get some of this data is going to come from the Tanabe-Sugano diagram, which I'm not going to hop back to right now. So all of this stuff here is going to come directly from the Tanabe-Sugano diagram, right? You're going to get this delta O over B, this E sub B for the first frequency, this E over B for the second frequency. And using all that data, you're going to get a calculated B value and then a calculated d orbital splitting. Okay, so all of this stuff right here, all of this stuff right here comes from the Tanabe-Sugano diagram. That's the actual experimental data that you're going to use to calculate that d orbital splitting. So that's one way that you're going to get this. The second way that you're going to calculate or determine this delta naught is going to be using the Jorgensen method, or the Jorgensen's method, which is kind of a basically chemists a long time ago, they had already determined these d orbital splittings, right, for a variety of these different cobalt complexes. The spectrochemical series had already been established, and so as a shorthand method to estimate this value without having to obtain spectral data, synthesize a new compound and obtain spectral data, Jorgensen came up with a method where you could estimate what that d orbital splitting is based on basically what's called a G value and an F value. So I'm going to go over this very, very quickly. You can read through all of this on your own time if you want, but this is basically, this obviously isn't the original paper, but this is basically talking about how you can relate. So first off, this talks about, just some standard, whatever complexes, vanadium, hexachloride, trianion. It talks about where the absorbance bands show up. And then it talks about how you can use those absorbance bands to basically calculate the d orbital splitting, all right? If you want to read all of this, you can go through it in detail. But basically what it does is, it says, okay, Jorgensen's method basically is just a method to predict what that is, what that orbital splitting is, as a function of whatever your metal ion is, okay, and whatever your ligands are, right? And so the way it does that is it says that this octahedral field splitting, okay, this delta zero is equal to F times G, so it's a very, very simple expression. And then these various values are tabulated for you, okay? And so the way you would do that, for example, is with, so we're dealing with the cobalt-3 complex. So this is the G value if you have a cobalt in the +3 oxidation state, all right? And then these are F values for the various ligands. Now, you'll notice that a handful of ligands are on there. So by default, water is listed at 1. And then these values move away from water, either more positive or more negative. You'll notice that as you get to something that's increasingly, well, it's kind of difficult because you have to deal with like both electronegativity and pi accepting ability. But in general, things that are good donors and weaker acceptors, you tend to get more positive numbers. Anions tend to go to slightly more negative numbers. Cyanide's kind of a weird one because it's a good pi acceptor also, as well as being anionic. But these numbers can be used to specifically calculate the delta naught values. So let me flip back over again. I apologize for jumping around a lot. For the ligands that you'll be using, we've already provided what the F values are, And then this G value is basically just copied directly from that other file. But basically what you're going to be able to do is go through, and like I said, all of this is the experimental data, which will get you all the way down to a calculated delta naught, okay? That's experimental, that's using the UV-Vis data. And then this predicted delta zero value is what you predict by just taking the F times G, okay? Now, there is one little caveat to that, okay? You'll find out if you go through and you calculate, if you use this value here, so let's say you're calculating this molecule right here where L is chloride, okay? If you take this G value and you take that F value for chloride and you multiply F times G, you're probably going to find out that that number that you get is going to be way, way, way different from the experimental. Can anybody maybe comment on why that would be so different?
Because you also have 5 amines.
Right. You've also got 5 amines. So even though this calculation is pretty simple, you need to take into account that you've got multiple amines on there. So the good news is you can basically treat the 5 amines in the cobalt one time and use that number over and over again. That'll speed up the calculation. And then so you'll have whatever this, right? So the amine is, what is amine? 1.25. So you'll have to do the 1.25 times this value. You're going to have to do that 5 times and add it in to then this value times that, or this value times that, or this value times 1.25 one more time, right? So you need to take into account that you've got 5 of those amine ligands on there as well, okay?
Do we average them? When you say added in, do you mean like average or all of them?
You'll sum them up. They're additive. It's additive. Yeah. It's pretty straightforward. You'll see. You'll see. So you'll add them all up and you'll get a number. As long as your spectroscopic data is pretty good. The only one that tends to be a little difficult are these two, and we'll talk about that in a few minutes. The rest of them should be pretty straightforward. You'll find out that they're within reason. But you'll be able to tell if something's like I said, really wrong if you've forgotten to add one of the ligands in or something like that, because it's going to be way off. Right, you're multiplying by a factor of 18,000, right? So you can be pretty far off. Okay, we will go over this again before you actually have to do your lab report. And next week we'll talk. I'm not going to do this at all today. Next week we'll talk about the magnetic susceptibility, because for one of the complexes, basically the one where L is NH3. You're actually going to measure the magnetic susceptibility of that molecule as well, and compare it to one. This is the standard, so you'll kind of compare it to that, but you'll actually compare it to a completely different molecule. And then what you're going to be able to do from this magnetic susceptibility measurement is actually predict, or not really predict, but take a measurement, but you'll be able to get the number of unpaired electrons in the system, and then you're going to say, hey, based on this number I got, right, does that make sense with this complex right here, which, as I've already told you, is cobalt 3 plus octahedral environment. So that's a D6 low spin system, right? And so you could already figure out, you know, right, D6 low spin, you could already figure out what that should be without even going through and measuring it. But you'll go through and actually take a measurement. And this won't take, well, I won't say that it won't take too long. This you'll have to, it does take a little while because the balance is super sensitive. If you like breathe on it, it's going to mess up your numbers and stuff. So just we'll talk about that next week before we do it. Okay, so that requires its own kind of a discussion. Any questions about this before we move on? And then the last part of class, we're going to talk about exactly what you'll be doing in lab in terms of synthesis. All right. So it is a pretty straightforward lab, right? You're making a handful of compounds. You're going to measure some UV-Vis data on them, okay? Though before I jump right into the synthesis, the one that's going to be the trickiest are these two compounds here, okay? Dr. Martin's probably talked to you about how you can have linkage isomers, right? Various, so cyanide, CN is one of those. CN can bind through carbon or it can bind through nitrogen. It almost always binds to carbon, but you can get it to bind both ways. nitro is the same way. You can have a nitro ligand or a nitrito ligand. And a nitro ligand is where it's inbound, nitrito is where it's O-bound. And so the nitro is the thermodynamic product. A nitrito is a kinetic product, basically, so this is less stable. So you're actually going to make some of this, and then you're going to, I should say, you're going to make some of this, but then you're also going to make some of this. And the problem is that over time, this will isomerize to that. And so when you make this, you need to kind of make it, fish it out, and get your UV-Vis spectra pretty quickly. I will say, what you guys are doing is much easier than what I did when I was a student. So I was the true guinea pig, right? I was Martin's first class ever. He had us make this and make this, and we actually monitored this isomerization. We measured the kinetics of it by IR, and so we had to make a KBR pellet of this stuff here, and we had to keep the same pellet, so the data would be consistent, but to keep the same pellet for like a week and take IR spectra every day. And if you've ever made an IR pellet, right, they're fragile, they're not exactly strong, right? And so we had to make sure like we didn't crack it, put it back in our drawer every day and take it out. So you're gonna make it, measure it very quickly. For the most part, it works. There will probably be one group, maybe two groups that have your UV-Vis data will be a little muddled because you'll start to have some of this already forming, and so you'll have a mixture of both of them in there. Keep in mind, you're going to have this pure, so you can always try to kind of subtract it out to figure out where it should be. But for the most part, it works. You just got to be kind of quick with it. Okay, so, all right, so what are we going to do? So the first week, we're going to make basically your two starting materials. The starting material is really the one where L is chloride, because chloride's a relatively weak field ligand. Okay, it's not the weakest, but it's relatively weak field. It's labile, right? So if we have chloride, we can add water to it, or we can add a nitrose source to it, or something like that, and we can knock chloride off and replace it with a different ligand. Okay, now to make the chloride, we're actually going to go through the amine, right? So what we're going to synthesize first is where all of these are amines. We're going to have some of that, and then we're going to take some of it and knock an amine off and replace it with chloride. This, even though this is a precursor to making that, this will not be the starting material for the rest of the reactions. This will be the starting material for the rest of the reactions. But you need to go through this to make that. Okay, so week one, we're going to make those top two compounds right there, where L is chloride and amine. And the idea is that you get them, hopefully you get them dry enough. Water's, usually you make these things in water, so it shouldn't be too bad if you have a little bit of water on there, but you want to make sure you get them hopefully clean enough to get your UV-Vis spectra of those two complexes, okay, week one. The next week you're going to synthesize the water version, the nitrito. I think this is, I need to fix this. This is a typo from Dr. Martin, but one of these should be NO2 and one should be ONO. And you'll collect the UV-Vis data for all of those complexes, as well as collecting the magnetic susceptibility for your starting parent compound, okay? So let's talk about kind of let me see where I'm at. Okay, let's talk about the chemistry of these things, right? Okay, so I've already talked about all this, right? This is talking about how we're going to be able to measure UV-Vis data to get the delta knot, okay? This sentence right here talks about why, how we can make this and how we can basically do ligand substitution chemistry on it. So in terms of the synthesis, and this is kind of key, okay, because it brings together several concepts that you've been learning since Gen Chem and more recently, of course, in Dr. Martin's class. So, excuse me, we're actually going to start with the cobalt-2 ion. So the chemistry begins first by oxidizing it. So we're going to oxidize from cobalt-2, excuse me, to cobalt-3. And the oxidant of choice that we're going to use is hydrogen peroxide, okay? So, you're going to be using the strong stuff, the good hydrogen peroxide. But you can only do this oxidation from cobalt-2 to cobalt-3 in an appropriate, oxidizing environment. You need to have an environment such that the complexes become kinetically stable, right? And so one thing that we often don't don't think about. I certainly don't think about it in the type of research I do. And this goes way back to Gen Chem, right? If you want to do oxidation chemistry, and especially if you're doing, like in the case of what we're doing here, we're going to change it not only from cobalt 2 to cobalt 3, but we're going to replace all these chlorides, right, with a bunch of different ligands, amines, water, you know, whatever. If you want to start to swap that out, though, you need to have it in an environment where any redox chemistry that takes place is favorable, right, or feasible. So if you consider the oxidation reactions, or the individual redox reactions of what's going on when peroxide gets reduced or cobalt gets oxidized, okay, these are just two examples. There's a lot of other examples we could look at, but if we wanted to try to run this reaction in water, so the idea here is we go from aqueous cobalt 2 to aqueous cobalt 3 with just water as a ligand, all right? Well, the redox potential of this reaction in water, okay, is negative 1.84. The redox reaction of just the peroxide is positive 0.117. And if you want the reaction to be feasible or take place, the sum, right, the net overall redox chemistry has to have a positive redox value, right? Overall, calculate the overall cell potential, the potential of the two draft reactions to be added together, and for electrochemical reaction to be spontaneous, the overall cell potential must be positive. So if you try to do this chemistry by oxidizing the cobalt in water, the problem is you're going to get a negative 0.1 or so, give or take, but you'll have a negative electrochemical potential. And so trying to do this oxidation in water is not a spontaneous reaction and therefore will not take place, okay? So it's really critical that you do the chemistry in the presence of ammonia, which is why ultimately what we're gonna make are these this hexaamine complex, okay? If you instead consider having amine ligands on it and you're oxidizing the amino complexes from cobalt 2 to cobalt 3, well, that has a cell potential, a redox potential of negative 0.1 as opposed to negative 1.8. So we're at negative 0.1 added into positive 1.77. That's a positive potential, electrochemical potential, and so that is a spontaneous reaction. So these reactions do have to be carried out in the presence of ammonia, otherwise it doesn't work. So that's kind of what that's talking about. This is just more of the same. Basically, this is just talking about how in the presence of a large enough excess of L, using the Chapman's principle, we can basically force substitution of one of these. And then we're specifically going to force it to be chloride, which is an easily substitutable labile ligand, and then we can swap out for water or the nitro group. And then the key thing here is the only situation where students sometimes run into trouble, I think we had this with one or two groups last year. Dr. Martin has seen it throughout his career, okay? The driving force for these reactions, okay, is the insolubility in water of these chloride salts. Let's say, okay, so the key here is when we make this molecule right here, right, I should say this ion, we could have a lot of different counter anions to go along with this. But if we have chloride as the counter anion, this complex here is insoluble and will precipitate out. And the same thing with all of these derivatives if we change one of the amines out, okay? So having chloride as our counter anion in the synthesis of these reactions is also very critical in terms of getting them to precipitate out of water and having something that you can filter and then isolate and get clean. So why do I take the time to mention that? Well, if you're having any problems, so you follow the prep, and this will happen at least one group. You follow the prep exactly as it's written, and nothing precipitates out. If that happens, add more chloride. Whether it's sodium chloride, because in some cases you'll be adding sodium chloride, in some cases you'll actually be acidifying the reaction with HCl, okay? Add more chloride. Add more HCl or add more sodium chloride. Get it to be a supersaturated solution in chloride. The chloride by itself, any aqueous form of chloride that you have, is going to be soluble in water. The idea is to drive the formation of this complex, or these complexes, right? Because you'll have a different L. Those will precipitate out, okay? So when in doubt, if you're not getting a solid to precipitate out, add more, whatever your chloride source is, add more of it. And that usually works. There might still be one group with one specific reaction that just has a time getting it out. What can I say? It's chemistry. You know, sometimes if the chemistry gods aren't on your side for that day, they're not on your side, right? But right, and that's kind of what this paragraph talks about. Okay, it's just talking about the KSP values and the solubility of the various chloride complexes in water. You can derive them out. And then, like I said, last but not least, we'll talk about the isomerization of the nitrite and nitrito, and hopefully that works. This actually talks about how the things can synthesize. They go through these, because the nitrogen-oxygen bonds have some double bond character, the nitrogen to oxygen linkage can basically rotate through a pi complex, right? You talked about pi complexes a little bit in this class, yes, no? Okay, so these things can basically isomerize from an O-bound, in-bound, or vice versa through these types of side-on complexes where the pi bond between the nitrogen-oxygen bond is interacting with the cobalt. All right, yeah, okay. So I'm just going to run you through the two procedures that you'll be doing this week. They work, guys, okay, they work. The only problem that you might run into is just making sure you add enough chloride to get the compound surface rotate out. So here's the first complex. Well, I won't say the first complex. This is the one that you're going to use to do all your subsequent substitutions. So this is where L is chloride, okay? So you start off ammonium chloride, in concentrated aqueous ammonia, which aqueous ammonia is this ammonium hydroxide, right? For those of you who don't remember. You can add this together, stir bar, you're gonna add your cobalt chloride hexahydrates, this is your cobalt 2. It recommends grinding it just to get a little bit better surface area, you know, smaller particles. Add it in portions while stirring. You're gonna get a kind of a nasty brown solution. And then at that point, your TA may or may not be given, you might be measuring this out yourself depending on how busy your TA is. But you're going to get basically 4 mils of 30% hydrogen peroxide. So I don't remember if you guys have worked with this stuff before in other labs, maybe you have, but keep in mind, right, this is 30% hydrogen peroxide. This is not the stuff that you go and get at Walgreens or whatever, which is 3%. Right, so this is 10 times more concentrated, and that might not seem like a lot, but pardon my French, this will fuck up your skin if you get it on you, okay? So be careful with this stuff, all right? This is not good. You don't want to mess with that stuff. Right, and so you'll get some hydrogen peroxide, and then you're gonna basically gradually add it into the reaction, okay? Basically, once all the gas evolution has ceased, you're going to add some HCl to it. That's going to help neutralize some of the base that you have in there, because the aqueous ammonia is ammonium hydroxide. The redox chemistry with the peroxide will generate more hydroxide. So the HCl is to start to neutralize the solution and add chloride, right? You're adding chloride to the reaction. Once your HCl has been added, you're basically going to heat it for just a couple of minutes. It's not a very long reaction. Add some water, cool it to room temperature, and you should get a slurry of your product. So this is a nice kind of a, I'm trying to remember, Gabby, so I know it says purple, but I think it's kind of like a purplish red, right? It's like a magenta color, maybe is a better description of this complex. But you should have kind of like a purplish red slurry, which you can then just basically filter over filter paper and collect a solid. Wash it with a little bit of water, ice cold ethanol. Ethanol, make sure it's really cold because it is soluble in ethanol, but that's also really important. It's going to help push the water off to allow you to get the complex dry in your lab period, right? So you can get the yield on it. If you don't get rid of the water and you're just sitting there, you know, with an aspirator pulling air over it, when you go to weigh and you calculate your yield, you know, at the end of class or whatever, you're going to have like, you know, 180% yield because it's got so much water stuck on it, right? So make sure you take the time to rinse it with the ethanol like it says. And then in another batch, okay, so right, and then that'll get you your 1 compound with the chloride, so you'll get a yield on it, and you'll get your UV vis measurement of that complex, okay? For where L is ammonia or amine, you're basically going to do a separate reaction. So you'll still be starting with cobalt 2 chloride, ammonium chloride, DI water, some activated charcoal, and then you're going to add your ammonium hydroxide again, so your concentrated ammonia. Basically cool it down, add your stir bar, and then you're going to then again begin the oxidation process, but you're going to make sure to keep it nice and cold this time. Again, same warning about working with peroxide. This is, I think, a slightly smaller scale, since this is not you're making more of this because you're going to use this to make your other complexes. Let you add your hydrogen peroxide in slowly. Make sure it stays cold. That's really important because that will mess up not only the product you make, but it's also going to mess up your solubility and things like that. Once your peroxide's been added, make sure you cool it back to 0 degrees, and that's going to allow precipitation of your product. Okay. This talks about, if you want to, about making sure you remove all your activated charcoal. But basically, it involves dissolution in some HCl, reprecipitation, washing again with some cold ethanol. Yeah, and so that's basically what you're going to do this week. So the reactions themselves don't take too long. So from start to finish, if you're being efficient, you can probably get, in terms of synthesis wise, let's call it 2 hours tops. I don't think it should take too much longer than that. While you get, make the first one while it's sitting there drying on your way in your Buchner funnel, go ahead and start the next one. Should take about 2 hours tops, and then that leaves you another 2 hours to get your yield, get your UV-Vis data and everything. So it shouldn't be too bad. Are there any questions about what you're doing this week? This is kind of a cool experiment, guys. I remember doing it as a student. The first time I taught it was last year. It's kind of cool, nice colored compounds. I think it's a really good, as much as I didn't want to teach it because I didn't remember how to read or do Tanabe-Sugano diagrams, right? I had forgotten all that. I think this is a very good experiment to tie back to what you're learning in the classroom. That's really, I think it's really important. So hopefully you guys have fun with it. And then next week we'll talk about the magnetic susceptibility part of the experiment. That works really well also. You just have to be really, really careful because it's super sensitive. All right, cool. Thanks, guys. Welcome back. Get back.